In the previous classes, we have discussed one-dimensional to two-dimensional transition. What are the new things that we encounter? Then how do we overcome those challenges? I proposed natural coordinates to make the whole process easy. We discussed how to do the coordinate transformation, interpolation functions for the field variable, all those things we discussed. At the same time, we also noted that the derivatives of the field variable that we need are in terms of real physical xy coordinates, for example, whereas now we have interpolated them using natural coordinates. So, derivatives from one coordinate frame to another coordinate frame we had to link through Jacobian. Okay. We saw how Jacobian is derived and all that. We have also done a good number of practice problems in the previous class. So, in today's class, what I am going to do is to see how we can now formulate a two-dimensional element. I have taken one particular domain as an example. In the textbook, I have discussed for fluid mechanics and so on. So, you can refer to the textbook for more details. Especially, I have discussed it starting from a governing differential equation. The one-dimensional examples that we have discussed starting from a governing differential equation were mostly ordinary differential equations because it is one dimension, right? Domain agnostic. Okay, we did not pay particular attention to any one particular domain like structural mechanics, fluid mechanics, heat transfer like that. Now, if you look back at the one-dimensional formulation, I have spent a lot of time in differential equation based formulation. I indicated how it is done if the formulation is in the form of minimization of a total energy functional expression. Here I will do reverse. I will spend more time to use the energy expressions, total potential, etc., because I have chosen structural mechanics as the domain. So, we can spend more time on that type of formulation. Then I will show how Rayleigh-Reed's method enables us to use piecewise continuous trial function approximations in two dimensions to formulate 2D elements for structural mechanics. In the book, in my textbook on FEM, I have also done extension of ODE to PDE and shown how to solve a problem of, say, fluid mechanics, for example. Okay. So, you can refer to that part there, but in the class I will restrict myself to only the structural mechanics problems, so that we can spend more time on the variational formulation. Let us see how it goes. You would now notice that while I was able to work out the details in the one-dimensional case, now we come to two-dimensional elements, it will not be possible for me to actually work out anything. I will only show how it is done. So, to an extent it makes you feel that you have not really understood it. Okay. But the only way to understand, master this, is to do the derivations yourself independently based on whatever we are discussing in the class, and actually even more is to develop a chota code for yourself, which is very simple. I will explain how it is done in the today's class or next class and so on and so forth. So, you should be able to develop a 2D finite element code with no great difficulty, and especially so if you have already done attempted 1D FEM code based on what we have discussed. Of course, when you solve course project problems using the software, then you will know more details of 2D and 3D elements, because you are actually going to use a professional software to solve 2D and 3D problems. So, let us get started. We will review what we have done from the point of view of structural mechanics. So, we looked at a simple 3-node triangle element. Now, when we say two-dimensional structural mechanics problems, please remember our earlier discussion. We are saying that the deformations are in one plane only. x direction is u displacement, y direction is v displacement for any point P in the system. It is subjected to forces only in that plane, not perpendicular to the plane, no deformation, no force. Perpendicular to the plane, stress may be 0, then it is a plane stress problem. Strain may be 0, then it is a plane strain problem, or this could be representing the element in a ring form. So, it becomes an axisymmetric. So, the variation is again only in this plane, like a cylinder or something. If I cut a section, so this is a ring, what I am seeing is the face of the ring. Okay. So, this is the context you need to imagine throughout the discussion. Okay. So, my emphasis is, if this is say along x axis, along y axis, any point can have u and v displacements. I am thinking in terms of a triangular element with 3 nodes. Say this is the simplest element and one of the very first finite elements to have been formulated. Okay. So, we should be able to easily understand it, I hope. Let us see how the discussion goes. So, I am taking a triangle. So, 3 vertices, each vertex will have u displacement, v displacement, u, v, u, v. So, 6 displacements, okay, which are unknowns for that element. So, therefore, I am going to end up with how many equations? For this element, I should end up with 6 equations. Okay. Then I will end up with, for all the elements, 6 equations each. I am going to assemble them together to get the system level equations. I will substitute the boundary conditions and then I will be able to solve. So, our methodology remains the same. So, for this simple triangular element, okay. Now, 6 equations in 6 unknowns I should get. Right? This is my aim. So, this will be 6 comma 1. So, therefore, this should be a 6 by 6, 6 comma 1. Since these are displacements, what is multiplying them, we would call it as the element stiffness matrix, and this we would call as the element force vector. Okay. So, my discussion right now is going to be towards estimating what is on the left hand side, what is going to be in the right hand side. But I won't really do it only for this element. I will also introduce some notation, some method which will be useful for other elements also, because this is a very simple equivalent of our linear rod element. So, we have seen what are the advantages and disadvantages of the rod element. This will be equivalent of that in 2D. Okay. So, let us understand what we are trying to do here. So, in the case of this 2D first element, I am taking the problem of structural mechanics. If you were to consider heat transfer, then each node will have temperature, and temperature will be a scalar field. In any direction, its temperature will be the same at that point. So, only one value of temperature, T. So, T will be given in terms of N1 T1, N2 T2 and T3. Here we are thinking of U and V being interpolated from their nodal values U1 V1, U2 V2, U3 V3 through the shape functions. This is the kind of problem you solved in the previous class, interpolation. I am not going to be satisfied with just this. I want you to get the notation also clear to you, start becoming familiar with the notation. So, the notation I am going to use is, at any point P inside, there will be 2 displacements, right? U, UP and V of P. So, delta at that point P will be in terms of u of P, v of P. That is x direction displacement, y direction displacement. Okay. This is interpolated, so I am going to write it like this. So, whatever is here, what will be the size of this thing? Because this is 6 comma 1, this will be 2 of 6, because this will be 2 of 1. Okay. The reason why I am emphasizing this is that now you will be, if you become familiar with this representation, you would be able to extend it to more complex 2-dimensional elements or even 3-dimensional elements. It really does not matter to us now once you start becoming familiar with this type of representation. So, a displacement at any point, in the case of 2 dimensions, there are 2 displacement components along x and y. In the case of 3 dimensions, it will be u, v and w, for example. This will be 3 comma 1. That is all that will be the change. Okay. The displacement field at any point within the element is interpolated from the nodal values of displacement. The nodal values of displacement in a 2-dimensional problem will be u and v. So, therefore, it is u1, v1, u2, v2, etc., etc. Because it is a 3-node element, there are only 6 of them. So, this is 6 comma 1. If I were to take a quad 4 element with 4 nodes, each node having uv, so this would become u1, v1, etc., etc. to v4. So, this will be 8 comma 1, but uv will remain the same for delta p. So, this will stretch to become 2 comma 8. Now, if it is an 8-node quadrilateral element, what will be the size of this vector? 8-node element, 16 by 1. If this is 16 by 1, because this remains still u, v displacements only, 2-dimensional problem. Okay. So, this will become now 2 comma 16. So, in general, I am going to simply represent it as delta is a set of shape functions into delta E. Delta E will now be of a size that can stretch depending on the element. For a simple 3-node element, it is 6 comma 1. For a more complex element, we have seen now 8 comma 1, 16 comma 1, whatever you want. In 3 dimensions also you can imagine. Okay. A 3-dimensional, so if you want to imagine element level analogy, for 1D this was, an analogy of this was the simple rod with node 1, 2, u1, u2. The 3D analogy of this will be, let me try to sketch. Okay. So, it is a tetrahedron. Okay. It is a tetrahedron. It will be, numbers will be maybe 1, 2, 3 and 4 here. That is a 3-dimensional analogy of this. Each direction x, y, z, because you have only 2 nodes, you would still have only a linear shape function, interpolation function. The first derivative, whether it is heat flux dt by dx kind of term or strains dou u by dou x kind of term, will be constant along x, y, z. So, it is throughout that volume of that tetrahedron, dt by dx kind of terms, heat fluxes will be constant, strains will be constant, stresses will be constant, etc. So, it is same element, shape functions are linear, therefore, the behavior will be similar. It is 1 dimension, 2-dimensional, 3-dimensional. So, since you are now familiar with natural coordinates and the derivative transformation, Jacobian and all that. If you understand this logic and the method, notation, etc., then extending it to 3D should not be difficult at all for you. So, I will not be discussing 3D in this course. We would rather prefer to introduce a time domain, because that will bring in some new challenges. So, once we are familiar with the 2D elements, instead of going to 3D, I will bring in time, and in fact, I will simplify it, go back to 1D and bring in time, because time brings in lots of new things, transient problems. So, I will discuss that rather than going into 3D elements. I assume that if you are carefully following me and you have understood 1D and you will now understand 2D, then extending it to 3D on your own should not be difficult to follow 3-dimensional elements, which probably you are already using in your course project. Usually all these packages will also give lot of theory manual. So, if you read the theory in that software, it will tell you how the element is formulated and all that stuff. So, please extensively study the theory manual of that software. They would also give some references which they have used to develop the theoretical framework, which is then used for the coding of the software. Okay. So, keep this point in mind. We are going to say delta is equal to n into delta E. This is my first generic notation now. This is going to be that delta, even though I have introduced the delta term because it is commonly used for displacements in structural mechanics. But if you are solving fluid mechanics or heat transfer or electromagnetics, you can give it interpretation as temperature or whatever you want. At any point in the element is interpolated from the nodal values of the field variable of that element. Therefore, E at the top through the shape functions, the sizes of the matrices will be stretched, okay, to suit that element. So, this is going to be my first I would say generic notation that we are introducing in the course. Okay. So, that is what I have written here. Is that clear? Now, let us see what we did for this element. Those were the shape functions linear in x and y. Okay. Alpha, beta, gamma are constants, delta also constants based on the coordinates of the element. We have seen how they are in a cyclic manner, x2, y3, x3, y2, xy coordinates of the nodes determine these constants. So, it is possible to evaluate them for a given element. Once you have done the meshing, the coordinates x1, y1, x2, y2, x3, y3 are available to you. So, you can compute these things. It is not a problem at all. Okay, fine. Now, what do we do? So, this is what I have explained to you now. I am going to use this notation, and this is how the n matrix will look like for this element. I have brought in, because I wanted it to be a 2/6 matrix, I have brought in between zeros. Okay, n1 0, n2 0, n3 0, like that. You can perhaps use some other notation, some other way of doing it and so on, but this is a convenient way of doing it, commonly followed in most books. So, that is what we are also doing. Is that okay? It is the same notation I used in my textbook also. Fine. Now comes the next step, strains. Displacement field is interpolated at any point. Now, I have to find the strain. My strategy is going to be like this. I have now taken some element. At a point, I am seeing the displacements. Those are interpolated from the nodal values. Okay. Now, I am trying to compute what is the strain. Next, I am going to compute what is the stress at this point. With this strain field and stress field, there is a certain strain energy in the deformation of the element, because the structure behaves like a spring. When it undergoes deformation, it stores elastic energy, and when the load is removed, it gives you back. So, our fundamental assumption, because we are doing linear analysis element structural mechanics, is that it is purely elastic. Okay. So, it will come back to its shape. So, I am going to use some of the assumptions of the structural mechanics theory that you have learnt in solid mechanics, that kind of courses. So, whatever we do, even though we are doing finite element analysis, even though you may use a million elements, those assumptions will still be limiting the results of our analysis. Okay. Keep that perspective also in mind. Just because you are using finite elements, you do not get any results better than the assumptions that you have made. Okay. For example, in this slide I am showing what is the strain displacement relationship. Now, how did you get this strain displacement relationship in structural mechanics? Because you assumed small deformations. Epsilon x is simply given as dou u by dou x. Those of you who have done solid mechanics would be familiar with this. Anybody who is not familiar with this equation, strain epsilon x is given as dou u by dou x. You can think in terms of this as elemental length dx changes, this end has moved by u, this end has moved by u plus du. So, the change in length is du upon dx, original length, change in length by original length at an infinitesimally small element level. That is what is giving you this, but we are assuming that the deformations are small. If you may use million finite elements based on this derivation, but if in the actual problem the deformations are large, you are not going to get accurate results, period. So, it is important for you to understand your courses on solid mechanics, heat transfer, fluid mechanics, electromagnetics, whatever is the field, how these equations came, what were the assumptions, what is the applicability of these equations before you plunge into finite elements. Okay. Just because you are using a most sophisticated software, a million elements, lot of computing power, you do not get any better results. Here, this is fundamentally a small deformation assumption, linear strain displacement relations. Only under that kind of framework you will get accurate results, otherwise you are goofing up. Is that clear? So, this is our strain displacement relations. There are 3 strains I am considering. It is a plane stress or plane strain kind of a problem, not axisymmetric. Axisymmetric I mentioned to you in one of the earlier classes. Like this, there will be one more strain, because in axisymmetry, if radius increases, circumference will automatically increase. So, you cannot have a situation with only 3 strains, 4 strains will automatically be there. Okay. But anyway, once you understand one formulation, you should be able to do others also. So, the 3 strains are given as epsilon x, epsilon y, gamma xy in terms of UVs and their derivatives. I am going to represent epsilon eventually in terms of the nodal values of displacements, because delta at a point is given in terms of some interpolation functions and nodal values. So, when I differentiate it, the B matrix that I am showing there, epsilon is B into delta I, B will contain derivatives of nodal displacements. Is that understood? Let us see how those derivatives are, how will you calculate them and so on and so forth. So, that will be the second notation I am going to introduce. Epsilon at any point, the strains are B times delta. So, this will be my second notation that I am going to use. Irrespective of any element, the metric sizes will increase, decrease. So, this may become 3, 1 or 4, 1 depending on axisymmetric element or a plane stress, plane strain element. Accordingly, this delta depending on 3 node triangle, it will be 6, 1, 4 node it will be 8, 1, 8 node it will be 16, 1. These will contain derivatives of these shape functions. So, this matrix will change. Okay. Let us see for an element how it would look like. 3 node triangular element. So, the strains are going to be like this. Please read it and make sure you understand what I am writing out. It will be dou u by dou x, right? So, dou n1 by dou x, because u is n1 u1. If you want, I will write it here for you. If you expand this, u is at any point p is n1 u1 plus n2 u2 plus n3 u3. So, therefore, dou u by dou x will be dou n1 by dou x, dou n2 by dou x, dou n3 by dou x. Fine? Is that okay? So, this will be a 3 by 6 matrix for this triangular element. The B matrix is derivatives of shape functions. Now, because n1, n2, n3 are linear in x and y, first derivative would become constant. So, B matrix would be just simply a set of constants for this element. We can easily compute that. Let me see. Those will be the constants. You remember the shape functions? Shape functions were these. So, dou n1 by dou x will be beta 1 from here. Dou n2 by dou x will be beta 2 and dou n3 by dou x will be beta 3. So, beta 1, beta 2, beta 3, of course 1 by 2 delta is common. That is what I have written here. 1 by 2 delta comes out, beta 1, beta 2, beta 3 in terms of derivatives with respect to x, gamma 1, gamma 2, gamma 3 in terms of derivatives with respect to y, and they are interchanged for the shear strain. Is that okay? Please feel free to stop me if you do not follow anywhere. But these are dependent on the coordinates of the nodes and these are constants, they do not vary. So, in the entire element, it is a constant. Therefore, the strain is going to be a constant. Therefore, the stress will be a constant. Like we had with one dimensional element, when you solve the problem, your approximation to stress will be like a staircase. This will be a two dimensional analogy. It would be like steps, okay, in a planar version of that. That is all that you are going to get with this element. Okay. So, constant strain, constant stress. Now, I bring in stress strain relations. I have found out displacement at a point, okay, and then I am now finding the strains. Next step will be the stress. Stress is given in terms of strain using your standard assumption of linear, elastic, isotropic, homogeneous. These four assumptions are made. It is going to be linear, elastic, isotropic, homogeneous. That is what you assumed in solid mechanics while you are deriving this. So, if in a given problem the stress strain relation is not like this, that means it is, for example, it is no longer linear elastic, it could be non-linear elastic, it could have entered into plastic zone. Deformation is so large, strains are so large, stresses are so large that it has entered into plastic deformation. So, any one of you who is from manufacturing background, okay, who is trying to do finite element modeling of a manufacturing process should not be using this relationship, because designers will tend to design any structure to the extent possible. It should not get into plastic zone. It should stay within elastic zone, get stressed, deformed, but recover when the load is removed. That is the designer's philosophy. So, he or she will kind of overestimate the loads, that is a factor of safety, and then design it. But a person who is interested in manufacturing that same car or whatever cannot manufacture it if the material does not undergo plastic deformation, cannot cause that shape, right. So, if you look at it in the form of stress strain graph, please keep this perspective very, very clear in your head. If you think stress strain curve will be like this, okay, designers will be only here. All the drama designers will do will be only within this segment. Manufacturing starts from here. Okay. So, you have to use the stress strain relations appropriate for your domain. Okay. I am simplifying the problem. So, it is inherently non-linear for manufacturing people, stress to strain relationship. Strains will be large, even the strain displacement relations that we have taken will not hold good, because it is undergoing large deformations. Okay. So, do not blindly use whatever we are discussing in the class, because you have to go back to the roots and then understand the governing equations, and accordingly you should use it. Even when you are using the software, it is better to understand what you are doing. Okay. So, this is our fundamental division between design and manufacturing, you should keep in mind. Okay. Different types of materials will have different curves, and therefore, you will have in your software that you are using even a choice option to give your own materials a stress strain curve, constitutive relationship. Okay. There is so much research that is done in constitutive modeling of plasticity theories, yielding and plasticity and all that. So, that you will gain by attending your manufacturing process courses. Okay. Assuming, going back to the safe net of design, where I am not even allowing the material to go into plastic zone, right? I am still in that zone only, I am a designer. So, I am trying to make sure that my bridge or my building or my machine will not go into plastic zone. This used to be okay in the past, for if I am taking the example of an automotive design. So, I keep giving this example, some of my undergraduate students who have done other courses are familiar. So, in the olden days, when a car gets into a crash kind of a situation, car would be fine. Okay. The car designer used to think that I have done a great design, but in all probability, all the passengers inside, including the driver, would have died. The whole energy of impact was being taken by the passengers. As our understanding of materials and material behavior improved, and our ability to model that, especially in the computer before we actually even do the testing, all these advancements, and with the growing realization that human life is more valuable than the car. So, we are now able to put in specific features in the car design by ourselves. By ourselves we are on design, we put crumple zones, so that actually when a car now gets impacted, it gets crushed. We will think that it is a very severe accident, which is true, but the energy of the impact has been taken into the crushing deformation of the material. That is the work that is being done and consuming all that energy of impact, so that the passenger is relatively safe. Of course, he has also been aided by seat belt, then the airbags, all such safety features. So, you have to see how the design paradigm has evolved over the decades. We are now able to put all these things into the system, computer, and analyze that. So, you have to apply appropriate model to develop your finite element for your problem. Okay, especially those who are doing DDP, MTP, PhD, etc., etc. So, if you are doing these things, then that is not really going to be anything new. Okay, these are all already known things. You are understanding, you are learning, so that you can build on it for your specific problem. Okay. So, this is a simple plane stress or plane strain kind of a model. I have taken specifically the plane stress, 3 stresses associated with the 3 strains. So, the stress strain matrix will be 3, 3. Okay. So, our model will be sigma will be d into epsilon. Now, why this should be called D? It could be called capital E elasticity, whatever it is. It's up to you. Whatever you want, you can call it. Okay. So, in this particular problem, now epsilon at any point is related to the stresses at that point through this stress strain relationship. This comes from Hooke's law, because we are assuming linear elastic isotropic homogeneous material. If it is a composite material, for example, it is no longer homogeneous isotropic material. It will be orthotropic, anisotropic. So, stress strain relation, it will not be simply one value of Poisson's ratio. Poisson's ratio in x direction may be different from y direction. So, you have to modify that matrix there when you use different materials. Not just the values, the matrix also may change. What will be a 0 or a non-zero in this matrix represent? It represents a certain coupling between one form of stress and another form of strain. When you have 0, 0 in the first and second row, third column, it means that the normal stresses are not coupled with the shear strain, which may not be true if it is a composite material. Which means, in practice, you have studied it in solid mechanics, it would mean that you cannot cause a normal stress without also at the same time causing shear strain, which means in practice that normal stresses and strains means you are only scaling up material, up or down, whatever. You are only stretching it, scaling up or down a material. You cannot achieve only that without also distorting the shape, because the material is anisotropic. Okay. Even though you think you have applied only forces that will cause stretching and compression, the shape will also automatically change because these are coupled. Then that 0 would vanish. Okay. Fine. Is that understood? So, this will be my third generic notation that I am introducing. Okay. But there is some issue with this relationship. Do you find any issue with this relationship I have written? Is this really Hooke's law? No? Who said no? Somebody said no. Yeah. Why do you think it is not Hooke's law? No, Hooke's law, we are still within the linear zone. There is no nonlinear part. Hooke's law is here. I am here. I am going up and down, coming back, going up and coming back, perfectly following the straight line. No, forget nonlinearities, because then I am not even in Hooke's law elastic zone. So, I am not even bringing that. Even if you are within the linear elastic zone, is there any issue with the way I have written stress strain relationship? Second order term, because I have assumed small deformations and all that stuff, okay, small strains. So, that is also okay. Even then, is there still an issue with this, or this is acceptable, I can move forward? Huh? Can I move forward assuming that this is fine? Those of you who have done a course on solid mechanics recently, mechanics of materials, whatever you call it, what does this equation indicate to you? A strain is there, a stress is there, because D is Young's modulus, Poisson's ratio, so some constants are given. So, a given strain is there means stress has to be there, or a stress is there means strain has to be there. Okay. So, when I am saying repeatedly, is there an issue with this? What should you think of? Okay, determinant is not 0, Baba. Okay, I am not taking a value of Poisson's ratio such that it is going like that. Okay, agreed. That is why you have a limit on Poisson's ratio and all that, right? 1 minus mu squared by 2 kind of terms are there. So, okay, agreed. Yeah. Relationship between shear modulus and Young's modulus is assumed in this, right? Because you would have done modulus of rigidity versus modulus of Young's modulus, some relationship including Poisson's ratio. So, I have assumed that incorporated it already. Okay. Engineering strains means what? Okay. So I am still here only. I am not going to necking and change in original area of cross section to current area of cross section, true stress, etc. I am still small stresses and strains. I am emphasizing this again. What does this equation point out to me? When I see an equation, first of all, A is equal to B into C. If C is there, A has to be there. If A is given, C is there. I mean, I can't be more explicit than this. In fact, actually, yesterday I was seeing a book titled The Art of Thinking Clearly. Yeah, somebody said interesting. What is that? Thermal effect means what?
There can be no strain, but there is this.
So, thermal cases, situations, I heat. So, I take a rod and I heat it. It undergoes expansion, thermal expansion. So, is there a strain? Yes. Is there a stress? Don't jump, don't jump, don't jump. When there will be no stress? If you are freely allowing it to expand, right? If you constrain it, it wants to expand, but you are not allowing it to expand, so there will be stress. By how much will be the stress? No, don't go to formulae. I hate formulae. Whatever you are understanding, you should be able to explain in language, simple words. So, if it wants to expand something, but I am saying that no, you cannot expand more than this, bas baba. So, it will try to expand, now it hits this wall and it can't expand, it wants to expand all the way here because I am continuously heating it. So, you can do a thought experiment on this. You imagine, that is how you must have learnt thermal stresses in basic mechanics course, that it has already expanded all the way here and then some internal forces have been developed which push it back. No, you can't come here, push it back inside. Like it's raining, the child wants to go out and play. So, he has actually, imagine that he has gone out, then his mother brings him back, holds his hand and drags him inside. No, it is raining, you can't go outside, and then closes the door. So, this is all that you are, so he will get angry and then throw tantrums and so on. So, stress always comes when you cannot do all that you want to do, you cannot achieve all that you want to achieve and so on and so forth. Okay. So, there will be strain, but not necessarily a stress. It depends upon the constraint. Okay. Similarly, you can think of a situation where there is stress, but there is no strain. I leave it to you to think of. So, you must think in terms of this type of a statement, which is a valid Hooke's law statement. Okay. Earlier one that we have written, epsilon is sigma is equal to d into epsilon, is valid only with the assumption, which we normally forget to write, that there are no initial stresses and strains, no thermal stresses, thermal strains, initial loads are not there. Like for example, you have taken a pressure vessel with there is a cap, and then you have tightened it with some bolts and nuts. All that you assume is initial loads over. Now I am putting pressurized gas into that. So when I am doing the analysis with respect to internal pressure, I am not including really all these bolts, nuts and this etc. Unless this will normally be not addressed in basic solid mechanics kind of questions, because you are not addressing interesting questions about at that level. You are not addressing interesting questions about whether the gasket, rubber gasket, is able to hold the joint well, or is there a leak of gas. If you are addressing that question under the pressure and probably even temperature, deformations have taken place. The metallic pressure vessel has deformed, the cap has deformed, the rubber gasket has deformed, the bolts and nuts have deformed under the load and the thermal, mechanical load as well as thermal load. Now, is the joint, what I should say, is the joint able to hold it? Still it's a true joint or not? Is there a leakage? Because leakage of poisonous gases will cause people to die here. So it's your job to figure out through, now it is possible through all these packages, you can completely do the simulation, okay, of leakage. Some of you can actually take it up as a course project or your BTP, MTP, DDP, whatever. You can actually simulate completely in the computer now with realistic properties of the gasket, because the rubber will have very different characteristics at different conditions. It's an elastomer, it will have different properties. And aging is another issue with rubber. You need to change your tires of your vehicle over a few years. After that you have to change it, whether or not you have run so many kilometers, because the rubber ages. And mistake commonly people do is not to touch the stepney, because isko to use hi nahi kiya, naya hi hai. Unfortunately, rubber doesn't behave like that. If you have not changed for 3-4 years, the stepney mein aisa hi baitha hua hai, so the rubber ages. So you need to change the 5 tires, not just 4 tires, is what they recommend. Why? Because of this. So it's possible to model that. All that will change is, in my approach of this type of notation, is this relation would have changed. Okay. You can still have a 3-node triangular element and so on and so forth. Shape functions are the same. What would change is just this relationship, and correspondingly the element equations would change. Okay, fine. So now comes, okay, I have displacement, I have strain, I have stress. So next is the combination of all of these things. Okay, when a structure is undergoing these many strains and stresses, what happens to it? It stores strain energy. That is, in one dimensional it is given as simply half stress into strain. Okay. In 2D you have 3 components of stresses rather than just one. So it expands to epsilon x sigma x, epsilon y sigma y, gamma xy, tau xy. And we have already addressed why that half factor comes, so I am not going over there. You have studied solid mechanics, so you know. So I want you to now start thinking in terms of this equation written not as an elaborate expression, but in a compact matrix notation as epsilon transpose sigma. Okay. So those of you who are not familiar with, so epsilon is epsilon x, epsilon y, gamma xy. Sigma is sigma x, sigma y, tau xy. Therefore, epsilon transpose sigma will be epsilon x sigma x plus epsilon y gamma sigma y gamma xy tau xy. That is what you would get. So, I am going to now onwards write only epsilon transpose sigma, not expand it. So, if there are 4 components of strains and stresses, whatever, it does not matter. If it is not even a problem of 2D, but there may be 3D stresses, then number of strains and stresses may be more, it does not matter to us. I am going to simply write epsilon transpose sigma, whatever be the size of epsilon, whatever be the size of corresponding sigma, does not matter. Half of epsilon transpose sigma gives me the strain energy for that problem. Okay. Now, sigma is given as d epsilon. So, I am going to write it as half of epsilon transpose d epsilon. Is that okay? Until this stage, are you with me? Clear? Okay. Now, I am going to kind of expand that, okay, for an element. So, sigma is dE, E is or epsilon is B into delta. B contained derivatives of shape functions, right? So, that is what. So, ignore the bottom half, I will come to the bottom half first, look at the top part. So, the strain energy in an element is what is integrated over the volume of that element. So, integral over V, what you are seeing in that equation is volume of that element. In this element, it is a triangular 3-node element we are formulating right now. So, the element is this, okay. So, this is our element. It is a thin slice of thickness T . It is extending to x1, y1, x2, y2, x3, y3 in xy plane. In the z plane, its thickness is small and it is uniform throughout. Thickness does not change for us, because that z dimension is not modeled at all for us. In this case, it is a plane stress or a plane strain problem. Okay. So, plane stress element I am taking, it is a uniform thickness T. Nothing is changing, displacement, strain, stresses, nothing is changing over the thickness. Okay. But still, whatever strain energy we are calculating, epsilon transpose sigma, integrated over this entire volume, is the strain energy stored in this element when it undergoes deformations u1, v1, u2, v2, u3, v3. Okay. So, that is what I am trying to compute in terms of the nodal displacements u1, v1, u2, v2, u3, v3. That is what is delta E. Now, in this case, you get the expression as epsilon transpose d epsilon. Epsilon is given as B into delta. So, therefore, you see how the expression has come at the, okay. Is that making sense? Now, I will go to potential of external forces. Now, the external forces could be like you have seen in yesterday's previous class solving a tutorial problem also. At any point, the force can be in 2 dimensions. Force can be along x axis, along y axis at any point. So, correspondingly, you have to calculate the strain energy or the work done by the forces, the potential of external forces due to forces that are distributed over the element, whatever is the force distributed, okay. And there could be concentrated forces. What we have discussed in the previous example in the tutorial class was at a given point there was a force of 8 kilonewtons, some 2 kilonewtons like that along x and along y, but it could be a distributed force acting, okay. So, we take it as the first term is corresponding to distributed force, the second term is corresponding to concentrated forces. The concept is the potential of external force is the force and the deformation of the point of application of the force, okay. So, that is what we did in the previous class. So, delta at any point I multiplied by the force being applied at that point Pi. along x-axis, along y-axis. These are scalar. Once you have multiplied force in displacement, you get work or energy, that is a scalar. That is the beauty of this type of energy based formulations. You do not have to worry about, once scalar, just keep adding them left, right, center. You do not worry about their directions, nothing. Okay. So, delta transpose Pi and correspondingly integral Q dV will be the distributed force over an elemental volume dV, and that point in that elemental volume is moving through x or y, and therefore it is doing so much work. That is what is in the potential of external forces. But delta at any point is given in terms of nodal displacement. So, I have put that n into delta, our first equation, generic equation, into the potential of external forces. So, the expressions look complicated, but conceptually if you understand, then you will be able to easily follow that. In this case, I have taken the forces to be independent of time, and so the deformations are independent of time. But when you consider dynamic problems like a vehicle going on a road, this building subjected to wind loads or earthquake loads and so on and so forth, dynamic, you got a good 30 on 30, 28 on 30 in mid semester, you jump up on your bench. So, that is a dynamic load on the bench, it has to be designed for that. Or you got 5 on 30, you are very bad, is that, what is this? So, it is a dynamic impact load, so you have to design it for that, right. So, then you have to take kinetic energy into consideration, which we have not taken into account in this case. So, for dynamic problems, next when I am going to introduce time domain I am going to bring in, I am already preparing you for that. All this formulation will hold good, except that energy expression will change. It is not just a strain energy, but I have to bring in also kinetic energy. We are now talking in terms of materials which have cross-disciplinary responses, like you apply an electric field, you will get mechanical deformations. That is what is that type of material? Piezoelectric materials. Or mechanical field, you will get electrical charges developed. So, it becomes a sensor. So, you want to find out what is the pressure. A pressure sensor is typically could be a piezoelectric sensor, and that is what is used in most of the foot plates. You want to help people with injuries to their bodies, athletes and so on. So, for rehabilitation, so you develop a foot plate which will have essentially a piezoelectric material. So, as the mechanical weight is applied, it develops some charge which is measured as the sensory output. So, you are able to figure out the pressure distribution over the foot, and as the person is walking, if this pressure distribution is not normal, so to say, so you are able to figure out that the gait of the person has changed from the normal gait, and that changes the distribution of forces in the body. That causes different forces on the joints, knee joint, hip joint and spine and all that stuff. So, you would try to bring the person as much close to the normal gait as possible. So, it is a piezoelectric material. Then here the cross coupling between mechanical and electrical terms of energy expression has to bring in. I have not considered anything like that. You have shape memory alloys. Okay, those of you who are thinking in terms of using shape memory alloys for your designs and all that. So, it remembers that at this temperature I was like this. If you change the temperature, mechanical deformation, whatever, when you bring it back to that, it kind of, we might forget, but that fellow remembers and then tries to go back to its original shape. So, all that will be captured by changing these energy expressions. So, when you look at your softwares like COMSOL, SANSYS, Abacus and so on and so forth, which do multi-physics problems using finite element analysis, how do they do it? Their change will be only in the energy expressions, external forces, force fields, then corresponding energy expressions, work done, all this part will change. So, there will be more terms, and therefore, at the element level equations there will be more terms on the left and right hand side. There will be couplings. A mechanical force causing electrical charge as output, an electrical field causing mechanical strains. So, it is actuator as well as sensor. So, all that will come in this particular single slide. Expressions will change. Is that okay? We are taking a very simple case for you to understand, because the focus of this course is to understand finite element formulation. So, I am not going into those details. If you are looking at such problems, the energy expressions for those problems you bring in and put it into this slide, then rest of it will be following same. Okay. So, now I add up all this, that is the total potential energy in the system. So, that is U plus V. It is still superscript is still E. E means in this element, because if you go back and see, my integrations are only over the small v. V is the volume of that element, okay, and delta ka superscript hai E element. So, that element nodal displacements only I am considering. So, it is still at the size of that element in my triangular element. Total energy I have calculated all this while. Now, for all the elements in the mesh, I have to add up the energies. Then I will get for the total structure what is the energy. Okay, is that clear or it is becoming messy? So, total with a Y, not I. Okay. So, total potential is giving a long expression. Please see how I have written it, how I have tried to group the terms together. While you are looking at these integrals and somewhat complex looking expressions, do not be overwhelmed by these expressions. Please keep in mind that delta with the superscript E is a set of nodal displacements that we have written here, U1 V1, U2 V2, U3 V3 for this element. These are the values of displacement at that node. They do not vary from point to point within the element, their integral mein nahi aate hain. These are values of displacement at the nodal points specific. So, I can actually pull it out of the integral. What is likely to vary within the element is that BD term, B for strain displacement relation, D for stress strain relation, depending on, supposing you are having functionally graded materials. Functionally graded materials means that you expect one portion of the material to withstand certain behavioral loads, thermal, corrosion, whatever, and therefore you control the material's composition, constitution to be able to withstand those. As through the thickness of the material, such effects are less and less. So, you will control the composition of the material, functionally grading the material properties. So, then within the element D will change from point to point. So, B, D are likely to vary, if at all, within the element. But delta E are the values of the displacements at the nodes. So, they cannot be within the integral. So, I can actually take them out of the integral. Okay. So, that is what I have done at the bottom. Whatever is in the integral, that within the red brackets is the matrix K. Okay. Let us expand and see what those equations are. So, if you focus on the first expression, B transpose dB, that is the integral over the volume of the element, delta E transpose and delta E come outside, because they are not varying from point to point within the volume of the element. They are the values of the displacements at the nodes. Okay, so that is the element stiffness matrix, and this is what is on the other side is all the distributed forces, concentrated forces, etc., which you solved in the previous class. That is the element force vector. So total potential is a summation of all of these things. And what did Rayleigh-Reed's method tell us? You minimize it, principle of stationary total potential. So that is what is the variational formulation, maximum or minimum of the functional. So first derivative has to be equal to 0 is the necessary condition. What are the variables in this? The nodal displacements. Earlier when we solved the problems, it was C0, C1, C2, C3, etc. Now it has become nodal displacements. Over a domain, over an element, how I can get different displacements and different strain energies, different work potentials, because within the element, how displacement varies, I have already fixed, it is a linear variation. So the only way I can bring in changes is by varying U1 V1, U2 V2, U3 V3. That is the only way now I can bring in extra strain energy into the system or extra potential of external forces terms. So the variation is possible only with respect to U1 V1, U2 V2, U3 V3 for this element. With respect to small admissible variations, the total potential has to be stationary. Therefore, dou by dou U1, dou by dou U2, dou by dou U3 should be 0. Dou by dou V1, dou by dou V2, dou by dou V3 should be 0. All that is compactly simply written as dou by dou delta has to be equal to 0. Okay. Then I get element level equations as K in E into delta E is equal to Fe. Why 1 delta E is coming? It is like half K x squared. K is the in between term, the stiffness, x into x, delta transpose delta. So it will be half K x squared ka derivative with respect to x will be x squared will be 2x. So half and 2 goes, you will get K into x. That is how you can easily visualize the process. Okay. Once you have got element level equations, assembling them to global level equations is following our usual process. Whatever we have done for 1D, it is a little more complex now. Node numbering will have to be done in this direction, etc. So the bandwidths will be larger, but process conceptually is similar. Okay. And then you have to substitute the boundary conditions, because otherwise right now this element equations cannot be solved because it is an element in free space. Okay. So it cannot actually undergo any elastic deformations. If you apply a force, it will move rigid body. It will move rigid body like this. Okay. By only constraining it through the boundary conditions, then it cannot move, so it undergoes strain and stress and strain energy and all that. So you have to remove that rigid body motion by constraining it, which is done through boundary conditions. Then only you can solve. Mathematically, right now the determinant of this coefficient matrix will be under 0. You will not be able to solve it. Okay. So you assemble the whole thing for all the elements like we did in one dimensional thing, then substitute the boundary conditions, then you solve. Now if you look at this particular element, why I said that this is the simplest element, one of the first elements, if not the first element ever formulated, will be evident from this slide. Okay. The B matrix is 3 by 6 is a set of constants. Okay. D matrix, once you are given Young's modulus Poisson's ratio, is a constant. So integral B transpose D B दिखता है बड़ा, लेकिन actually it is a constant. What is the size of this constant matrix? What is the size? You will see that B transpose D B, B is what? 3 by 6. This is 3 by 3. This is therefore 6 by 3. So when I do integral over the volume, this will be a 6 by 6 matrix. Six by 6 will mean 36 elements, right? 36 integrals if I evaluate, I will get one element stiffness matrix. Okay. For any problem, I may need many elements. So for each of the element, I have to do this 36 integrals. Fortunately for us, with this element, B and D being constants, everything is become a constant. So whatever you are seeking of dV, this is actually T into dA, because nothing changes over the thickness. So T dA, okay. Integral, that constants everything, if you pull out, integral dA is the area of the element. So I get 2 delta, that area of the element. So it's fairly straightforward to write it out now. Still it is 6 by 6 matrix, दिखने में भी दिक्कत है. You will have to write 6 by 6 coefficients. For more complex elements, your B, even if D is the same material, just aluminum, steel, plate, whatever, assume it is linear, elastic, isotropic, homogeneous, no variation from point to point within the element. D is fixed, but B will change. B depends upon the derivatives of the shape functions. If shape functions are higher order functions, then their derivatives will be varying from point to point. So B transpose dB will have to be evaluated. So if you think in terms of an 8-noded quadrilateral element, okay, what would be the size of B matrix for that? 8-noded quadrilateral, so 16 by 16 matrix hoga finally. 16 by 16 matrix will have 256 terms. So 256 integrals, each integral varying from point to point in a complex shaped element, 8-noded element. You have to do this double integral over the volume. So double integral, etc., t times dx dy. That is why we introduced natural coordinates, because now the integral will be in terms of zeta eta coordinates, -1 to +1 square domain. That we will do when we go to higher order elements. Okay. Is the flow clear? In this element, it is very simple, B transpose dB being constants. Computational effort also should become clear to you. Okay. This 6 by 6. Okay. Even if you were to take a simple problem, very simple problem, say I take so many triangular elements, let us say that it is subjected to some loads. I am trying to find out how much is the deformation. Even if such a simple problem I am trying to solve, how many elements are there? 1, 2, 3, 4, plus 4, 8, 12 triangular elements. How many nodes are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 nodes are there. 12 nodes, each node having u and v displacement. So when I assemble them all equations together, what will be the size of my matrix? 24 by 24. So I will not be able to actually solve any problem in the class. You also will not be able to solve any problem by hand. Okay. If you are required to do it by hand, then FEM wouldn't have become this popular. You wouldn't have subscribed to this course. Okay. We require a computer program to even formulate an element matrix, assemble all the element matrices, apply boundary conditions and solve all these steps. It is not just question of solving finally Ax is equal to B, which was the case in one-dimensional problems. One-dimensional problems, at least all this we could do. Assembly also we could do. It's only a question of solving a large A by Ax is equal to B kind of a problem. You needed some Gauss elimination based solver, which readily tools are available, you can solve it. But here that is not just that. You have to take recourse to some program which will help you do the integrations and formulate the element level matrices, assemble all these things depending on the configuration of the domain. Okay. Now imagine if it's a plate with a circular hole in between. So I will need to take a lot more elements to capture that circular hole geometry accurately, because stress concentration will depend upon that circular hole. Or if there is a crack, imagine those of you who are involved in fracture mechanics oriented research. So if there is a crack, then it's a minute crack, right? Like a hairline fracture crack. Then you will have to resolve that crack. What should be the elements? What should be the mesh density there? Imagine. For all that, you need to be able to compute the element level matrix, do the assembly, and then apply the necessary boundary conditions and then solve. Without recourse to a computer program, there is no way you can do this. So therefore, if you look back at the history of development of the subject, even though the conceptual clarity was there, Galerkin's method, weighted residual method, Rayleigh-Ridge method, it's all known, but in order to be able to implement it, actually take a system like a vehicle or a building or a bridge, an airplane, missile into the computer, do a digital twin of that into the computer, put everything into that and do forces and find out the loads and deformation strains indices could not be done till hardware and software platforms evolved. Okay. So see the coexistence of these, co-development of these two frameworks. FEM became so popular only because of, alongside the computer hardware and software, memory, everything, GUI, interfacing. Okay. When we learnt, if we had to imagine how it is done in 3 dimensions, then we had to actually make a model using cardboard or something like that. Imagine how these things were discretized, how they are put together again, etc. The GUI tools were very primitive. But now you would be able to render using all these softwares, and any view you want, you can cut it, see it, do the meshing, all that. So these are interlinked developments. Okay. So we will continue from next class with respect to how I would evaluate these integrals, how I will do rest of the calculations. Okay. Okay.